Welcome. Our project name is AllState Claim Severity. I'm Darin Chambers, and my teammates Matt Grover, Jay McKinley are here to talk to you about our data challenge. The topics we're going to cover today include an overview of the Kaggle competition for AllState Claim Severity, a walkthrough how we looked at the data as well as preparing it for modeling, what modeling approaches we used, our outcomes, and what are our next steps to finalize our project. The AllState Claim Severity is a Kaggle recruiting competition. The observations represent unique insurance claims with the target variable being monetary loss. There are 130 predictors in the data set, of which 116 are factor variables and 14 are continuous variables between 0 and 1 representing percentages. The data set is split between training set and a test set. The training set has 188,000 observations. The competition is based on mean absolute error, and we will be using this for our challenge. All data sets are complete. There are no missing or NA values in the entirety of the data.
The greatest challenge and novelty of this problem is that no domain knowledge can or will be available due to the lack of informative labels. As such, our modeling approach cannot focus on description, but must focus on prediction. Additionally, we can compare our models against others since this is an active Kaggle competition. Our success criteria for this project was a MAE below 1200. The current leaderboard has an MAE of 1097. The loss feature is skewed for this dataset. To accommodate for this, a log base E power transformation was performed, and that is called log loss.
As stated earlier, the challenge with this dataset is that none of our predictors have labels. Therefore, to better understand the relationship between log loss and each of our variables, we created two visualizations. One being a histogram to understand the distribution by category of each variable, and the other being a box plot of log loss against each variable. Neither of the techniques showed any variation of log loss for each of the variables. For the continuous predictors, we also did two visualizations, one being a kernel density plot, and the second being a plot of the log loss against the variable. Much like the factor predictors, we were unable to detect variation on any one variable. But with the kernel density plot, we did see that there was a potential for transformation, so we did some additional analysis. That additional analysis looked at symbox plots for a ladder of power transformation, looked at box Cox, did some skew and kurtosis analysis. We decided that we're looking at a prediction as opposed to a descriptive model, that transformation was very important for our future modeling approaches. So we transform based on the box Cox optimization for each continuous variable. We found that the transformations improved our model performance.
A random forest was used on a sample of training data to see if specific variables could be identified for future models. While many of the variables were identified, very little variance was observed with this. To additionally explore this option, FAMD, or factor analysis on mixed data, was attempted to better understand and to reduce dimensionality. FAMD is a generalized version of PCA, or principal component analysis, that combines categorical and continuous data. Unfortunately, it was found that very little variance is in this data set, with approximately 1.3% of the cumulative variance being explained by the first principal components.
Part of being a good Kaggler is trying out lots of different techniques to see what works best. We had a pretty large challenge with trying to minimize our features or to engineer new ones. However, not even the best models were performing well, with an average error at almost a third of the mean loss value. Our intuition is that no single model is going to get us a great score, and that some sort of model blending will be necessary, and of course lots of trial and error. To begin model testing, we first created a training and validation set out of our original large training set. 75% remained in the training set, while a random sample of 25% was extracted into the validation set. This validation set was then used for local validation of our training results, which were used to weed out the models that were not performing well with this data. We tried a variety of models on our data. However, as we suspected from our data analysis, linear models performed relatively poorly. However, tree-based models performed quite well. SVM is not listed because we were never able to get it to converge and produce results. In the end, the best models were extreme gradient boosted machine, and later on we added neural nets, which turned out to be extremely useful in the blending process. Once we had determined our best scoring models, we began doing hyperparameter tuning in order to determine which parameters optimized the models we chose. We continued to use cross-validation to avoid overfitting. From these 138 models, we chose the best based on how well they performed on the validation set and used them to predict on the final test set. We ended up selecting only 8 models that scored under 1,124 for their MAE. This selection outperformed the 20 or so models that were below 1,125 MAE and the 3 that were below 1,123 MAE. We initially submitted a few single models and some blends of homogeneous models to the Kaggle competition. For example, this is our first entry of a single untuned XGB model which scored 1,200 mean absolute error. Subsequently, we began seeing modest improvements in MAE once we began combining heterogeneous models, and our biggest jump came when we began averaging across a variety of neural nets and extreme gradient boost models. This last submission combined 6 XGB models and 2 neural nets, and though the best of these only had an MAE of 1,119, combined they were able to score 1,113. This is a fairly significant improvement by combining the models. In the future, we will be dropping gradient boosted machine and adding more extreme gradient boosted machines as they are performing much better. We'd also like to test using models as features in a second layer of predictions, and we'd like to use the extreme gradient boosted function create feature in order to try to squeeze a little more movement out of the leaderboard score. The last part of our presentation, we'd like to talk about a few useful tools we used. The first is FactoMiner, which was used for the factor analysis with mixed data. The next was XGBoost, which was used for extreme gradient boosting, which is a really powerful way to do tree models. The last is H2O, which is a really powerful tool for doing deep learning or gradient boosting. We used it for the neural nets, and it's quite powerful and quite simple to use. Lastly, on behalf of Darin, Matt, and myself, I'd like to thank you for watching our video. On this slide is my email address. If you have any questions about what we have done, feel free to contact me.